This time we'll be looking at a type of motion called simple harmonic motion. We have looked at motion, we have looked at circular motion, which is a type of motion. We'll look at the kinds of circular motion, the vertical circular motion, the horizontal circular motion. And today, emphasis will be on this type of motion called simple harmonic motion. So we want to look at what is this simple harmonic motion. Simple harmonic motion is a periodic motion that repeats itself at regular interval of time. And in this case, the object that is performing this simple harmonic motion normally oscillates about an equilibrium or a fixed position. And the acceleration of these objects performing this simple harmonic motion is proportional to the distance from the fixed position. So what are the examples of this simple harmonic motion? One of the examples is the swinging simple pendulum. That is one of the examples. We also have an example like the loaded spiral spring. Mass is attached to the spiral spring, and by the time you displace it, it will be performing simple harmonic motion. So we'll have some things like the tuning fork. When it's made to vibrate, it performs a simple harmonic motion. So these are some of the examples that we can talk about. And when you come to look at it, let's pick one of this. This is a swinging pendulum where an inextensible string is involved. Inextensible string. Assuming this is the string, you have the mass here. Remember, this mass is acting under the influence of acceleration due to a force of gravity. So it's under the influence of G. So by the time you displacing through a small angle, theta, that is the angular displacement. By the time you displace it, it will oscillate. And there's what we call restoring force. What do you mean by this restoring force? If you displace this and release it, it will swing over a time, and then the amplitude will keep on decreasing until at a point it will come back to its resting point, or what we call the equilibrium position. So if you also displace it, okay, let's look at this. This is the equilibrium point where there's no displacement. By the time you displace it, you have this restoring force. This displacing it on the right. If you displace it on the left, the restoring force will also be there. So assuming this is our A, B, C. This is A stands for the point where there's no displacement. It is in its equilibrium position. Displacing it on the right with a small angle, it oscillates. And displace it on the left with a small angle, it also oscillates. So assuming we have a complete system here, I will call this A, B, C. So if you displace it from A, it will oscillate, move through B to C, that is performing half a circle. By the time it comes back from C through B to A, it has performed another half circle. So we're talking about a complete circle. So when we're talking about one complete oscillation, we're referring to one circle. And there are some of the terms or concepts that we need to understand before we can fully understand the concept of simple harmonic motion. Like we talk about the amplitudes is the maximum point of displacement, amplitude. The maximum point of displacement, and is measured in meters. Remember, in performing this a simple harmonic motion, the amplitude, the angle of displacement should not be too large and should not be too small. Then we also have another term we call period. Is the time taken for one complete oscillation. The time it will take this bulb to move to C and back to A. The journey starts from A through B to C, then back to A. That is one complete oscillation or circle. So the time taken for one complete circle or oscillation is what we call the period. And it's given as 1 all over F. As T, period T, is given as 1 over F. Then we also have what we call frequency. F is 1 all over T. Frequency, the number of circles or oscillations completed in 1 second. And it is measured in hertz. Period is measured in seconds. But if length is involved, we can say that period is equal to 2 pi square root of L all over G. If length is involved, then period can be given as 2 pi to square root of L all over G. So we have a problem here to look at. And the problem says the length of a simple pendulum is 0.36 meters. And it is released at an angle of 10 degrees to the vertical. Calculate 1, the period of the motion, and 2, the frequency of its vibration. So looking at this, we can say that the length is given as 0.36 meters. And remember, G is a constant and is taken as 10 meters per second square. So we can appeal to this formula. T is equal to 2 pi square root of L all over G. which you can write as 2 times 3.142 square root of L, which is 0.36 by 10. So we can evaluate this and say that 2 times 3.142, that's the value of the pi, square root of 0.036. So by the time we take the square root, by the time we take the square root of 0.036, we have 0.1897. 0.1897 times 2 times 3.142. So evaluating this, we have 1.192, 1.192 seconds. As the first one. Then the second one, we talk about frequency, which is 1 all over t. So in this case, we have 1 all over 1.192. So by the time we evaluate that, we have 0.839, 0.839 Hz.